Today I'm going to introduce you to planets outside the solar system. And I'm going to organize my talk largely by detection techniques. And detection techniques, understanding detection techniques is important for understanding exoplanets because we don't have a random sample of exoplanets. Our understanding of exoplanets, and especially the numbers and types of exoplanets, is strongly biased by detection techniques, since planets are so hard to see around other stars. And if you don't have a good understanding of these techniques, or at least of the biases that they produce, then you can get a misleading impression on what kind of planets are out there around other stars. For instance, no Earth-like planets have been detected around other stars. 0. Nothing as small as Earth and as far away from a star. That doesn't mean that such planets don't exist, or even that they're rare. It just means that they're extremely difficult to detect, and we don't have the technology for it yet. I will go through the techniques. The first one to be successful, which was pulsar timing in the early 1990s. Then the one that really opened up the field, because it's led to discovery of planets around regular stars, not just dead stellar remnants, which is the radial velocity or Doppler technique. These techniques detect planets by the motion of the object they orbit towards and away from Earth. For more than a century and a half, people have attempted to find planets around other stars by the motion these other stars have against the plane of the sky relative to the positions of other stars on the sky. That's astrometry. And then there have been the other technique, which is the most important. Astrometry has not successfully found a planet yet. Transit photometry. This is looking just for the planets where we orbit, where we lie very near their orbital plane, such that each time they orbit, they partially eclipse their star. And these partial eclipses are known as transits. And photometry is just measuring the bulk amount of light around the stars and seeing how that changes with time, with these little dips every time the planet goes between us and the star. Another technique, which has found a couple dozen planets, is microlensing. And this relies on the gravitational bending of light. Then some planets have also been found by the way that you might first think of, which is direct imaging. Actually taking pictures of them. But that's only for very bright planets very far from their stars. And you might wonder why a planet far from its star can be bright, how that can happen. Well, these are actually young, very massive planets that are shining in the infrared through their own luminosity that's resulting from the heat of their formation and contraction. The 4 giant planets in our solar system emit about twice as much energy as they absorb from the sun. And the difference is from the cooling from the heat of their formation. And these planets that we're imaging directly are younger and more massive, so they're releasing a lot more energy. And then, my next lecture, I'll talk about Kepler results. Exoplanets has captured the imagination of the general public, and the reason exoplanets the field has captured this interest is because of astrobiology. Now let me elaborate on the individual techniques a bit. Pulsar timing, what this is think of planets as, well, first of all, pulsar is a stellar remnant. It's a dead star. It's called a neutron star, but it's not a real star in the sense that there's no fusion going on. A neutron star is about typically 40% more massive than our sun, and about 5-10 kilometers in size. So extremely dense. In some respects, it's a giant atomic nucleus. And a pulsar is a neutron star that is magnetized, it's rotating, and its magnetic field is not completely symmetric. There's parts of it that radiate energy, the radio wave, like, and since it's rotating, this radiation, sometimes we're in the beam and sometimes we're outside the beam. And so what we see, because of the rotation and the asymmetry at the neutron star, is we see pulses of energy from the star. And some of these pulsars, including the one where the first 3 exoplanets were discovered, are extraordinarily good clocks. The ones without planets, which are the other dozen or so of this type of pulsar, when they were found in the 80s and 90s, they were the best clocks anyone on Earth had. They were better than the best atomic clocks. Now, the technology with atomic clocks at keeping time has improved. The technology for pulsars keeping time hasn't changed. So the atomic clocks are now ahead again. But it's amazingly well spaced. That's because these things are old, so they're settled down, but they got some extra angular momentum by accreting material from a disk. Probably they had a stellar companion that was tidally ripped apart, and they accreted some material, therefore they're spinning roughly 1,000 times a second. They're called millisecond pulsars. And for this, one of them that disk presumably formed 3 planets. And 2 of them are a little bit more massive than Earth. One is about the size of the moon. Their orbital periods are all less than 100 days. Very exciting until recently. They were the 3 smallest exoplanets known. And the moon-sized one probably still is the smallest exoplanet. But turns out most pulsars don't have planets. And there aren't that many pulsars of this quality in terms of clocks so that we can detect such small planets. So a few have been found around other pulsars, but there are much bigger planets. Then there's radial velocity. Now, the pulsar timing, the thing is, the planets go around the pulsar, but really, the planets and the pulsar all go around the center of mass of the system. The planets are much lower mass, so they have much bigger orbits, but the pulsar still moves in little ellipses. And the part that when it comes a little closer to us, the pulses arrive sooner. When it's a little farther from us, the pulses arrive a little later, just because light travels at a finite speed. Now, radial velocity is looking at the spectrum of a normal star and measuring its velocity from lines, from the Doppler shift in the lines. So it's basically the same thing as pulsars, except you're measuring the velocity instead of measuring the change in position. And this has been enormously successful. At one time, well over 90% of the planets, exoplanets known, were from radial velocity. No, I don't need a software update. Good old computer. And this has found planets not that much larger than Earth, not that much more massive than Earth. Now, with radial velocity and with pulsar timing, you're measuring just one component of the motion of the star. And you can't tell whether the planet is in the same plane, in which case you're measuring the full velocity of the star, or is orbiting near edge on, in which case you're only measuring a very small component of the star's velocity. So you're getting a minimum mass. Now, in the case of the 2 larger planets around the pulsar, they actually got such precise measurements of the pulses. It wasn't just the ellipses of the planet's orbits that could be discerned, but changes in those ellipses resulting from the planet's perturbations on one another. And therefore, the masses themselves could be discerned. For radial velocity, there are 1 or 2 systems where you can get some idea of these perturbations. But in many systems, people have observed the planet actually transiting, which implies that the orbit is nearly edge-on. Now, astrometry, you can, in principle, find Jupiters from from a single telescope on the ground, sub-Jupiters from an interferometer, and smaller planets from space. The first announcement of an exoplanet discovered by radial velocity, by astrometry, was in 1859. It was wrong. There was another one in 1895. It was wrong. There was one in the 60s, and then another one in the 1960s. It was wrong. I remember when I was growing up seeing a couple announcements, and these were all the first exoplanet discovered with astrometry. It was wrong. When they started finding planets with radial velocity, they were trying to use astrometry to determine what the tilt of the orbit was. And they made several claims. And let's put it this way, they've been at this for over 150 years, and they still have a perfect record. Nothing right. I think they're going to break that record with the European Gaia satellite. I mean, that's much better astrometry for over 1 billion stars, although the ones that aren't that close won't be useful for this. But that's a record that I think would be really nice to see broken. Okay. Transit photometry. This is the partial eclipses. And it's found from the ground, smaller than Neptune, even smaller from a small space telescope the French launched a little before Kepler, and then much smaller. The smallest planet known around a normal star is not Mercury, but it's an exoplanet found by Kepler last year. And Kepler now has found the majority of planets known. And really been a wonderful mission, and I will talk about that in my next lecture. Microlensing is the gravitational bending of light as predicted by Einstein's general theory of relativity. And what's going on is you have a very dense star field. You look at this 10 million stars, observe them for a season, it's about 8 months, and you look for cases where a star starts to brighten. And it's brightening because another star is coming between us and this, what's called the source star and the lens star. And when this type of what's called a lensing event is seen, then people from all over the southern hemisphere start looking at that one target and trying to do very precise, very high cadence observations. Most of this is done in Chile, South Africa, and Australia, but to the extent that you have a decent site in Brazil or Argentina, it's also good. You know, small telescope is all you need. They detect these short time variations. The lensing events tend to be weeks to months. But if this lensing star has a planet orbiting in it, if the planet comes really close to the source star, as seen, if the star in other words, if the line of sight of the light from the source star goes really close to the planet, then it can affect the amount of light for a few hours. That's why you need a lot of observing stations. And that reveals these planets, and it tends to reveal smaller planets farther from stars. So although the two most successful methods by far are radial velocity and transit photometry, they're great at planets far near their stars. Both decline with distance. Transit more extremely than radial velocity. Microlensing is better for planets at about a few times the Earth-Sun distance. And that's just geometry and the distances to the typical good populations of source stars, which are near the galactic center. Direct imaging, taking pictures, also has a comparable number of planets. They're all very massive, several times Jupiter, and they are all significant distances from their star. There are two new instruments online in Chile. The Gemini Planet Imager GPI, which is the US instrument, and Sphere, which is the European instrument. And they're both starting up basically this year, and we should see a lot more images because they have much better resolution. They're very good at removing the light, the background light, and blocking off the light of the star. Because the planets, even these bright planets, are still like 1/millionth the brightness of the star. That's better than Earth, which is 1/billionth the brightness. Okay. Doppler shift, star moving away. Redshift, the star moving towards blue shift. These are theoretical curves that an observer would see in the plane of Jupiter's orbit. The response of the sun, the radial velocity response of the sun, relative to the pole of Jupiter. And you can see that got about 12 meter per second amplitude. Looks pretty much like a sine wave because Jupiter's orbit is fairly close to circular. Periodicity, that of Jupiter's orbit, just under 12 years. Now, if we add Saturn, so this is Jupiter and Saturn, you can see there's kind of a modulation on the 30-year period of Saturn. About 2 meters per second amplitude of that modulation. Saturn is less than a third Jupiter's mass and is a little bit farther away. Both reduce the amplitude. And then this is Jupiter, Saturn, and the rest of the planets. And you can see the same basic pattern. You can see these tiny wiggles of tens of centimeters per second due basically to Earth and Venus. And this just compares the three sets. You can barely see any difference between the red and the green curves, except in these little things here. But, so, now, people can get down to maybe 0.5 meter per second under the best circumstance, the brightest, calmest stars, typically it's more like 1 to 2 meters per second. So there's potential of detecting a Saturn analog, observing for long enough. Jupiter analogs are relatively easy, but it's pretty hopeless for Earth analogs. And also, you don't see any signs of Uranus or Neptune. They're like barely there. This is an actual light curve taken in the early years of success of radial velocity. We have a planet which is in a 2-year plus orbit, quite eccentric, and minimum mass 60% above Jupiter's. The eccentricity manifests itself in this being highly non-sinusoidal. You can see that the uncertainties there are plus or minus maybe 8 meters per second. So at that time, detecting Jupiter, very difficult. And we have to, so there aren't that many stars where there's enough data to detect the Jupiter, because it took a while for them to get that type of precision. And that's the orbital period, the wobble amplitude gives the mass, and not sinusoidal because of the eccentricity. This is a plot of the first 29 planets discovered with RV. And they're ordered by orbital period or semi-major axis of the innermost planet. At that time, there was only one system with more than one planet, Upsilon Andromedae. These planets are typically Jupiter masses. There are a few that are less than 1 Jupiter mass, but they're all at least 0.42. And the ones out here, more distant ones, are all multiple Jupiter masses. Now, a lot of people still have the impression that these are the common exoplanets. These inner Jupiter mass planets with semi-major axis of a 20th of an AU. Or maybe these eccentric Jupiters with semi-major axes of 1 AU. Well, they were the easiest to detect with radial velocity. They're not that common. This type planets are seen around about 1 in 200 stars. This type planets are seen about 1 in 15 stars. The Kepler planets I'll be talking about in my next lecture are seen around about 20% of stars. And even with Kepler, we're not seeing the smallest planets. We're not able to see planets like Earth, unless we were extremely lucky that we happened to be in the right place, and the planets had to be in the right place. We wouldn't see any of the giant planets. This is a somewhat more recent radial velocity, and it shows still they were getting a lot of inner planets, but more distant ones beyond 2 AU that were down at a Saturn mass or so, one way out at 9 AU. So it's getting less biased. 3 with 2 planets for many years I showed this view graph. I said, well, this is the number of planets found. And because it was kind of in the right ballpark, and there are some discoveries which are controversial. Excuse me. But now we're way beyond that. It's hard to figure out. That's a few hundred. We're now at over 1,500. Kepler alone is approaching 1,000. This is the mass distribution of radial velocity planets. These are bins of a factor of 2 in mass. So read here, between 1 and 2 Jupiter masses, there have been a little over 160. And mass, by mass I'm saying, meaning here, m psi I, the minimum mass. So you see the peak at Jupiter mass. It's a fairly broad peak. There's a drop off here, because even though we have better precision now, some stars aren't as well behaved, some groups don't have the precision, and these planets can be, for a given precision, these planets can, the more massive ones, can be detected at greater distances. So there's a real drop-off, and it's actually steeper than what we see. What's apparent here. Now, this, going down on this side, is a result of observational selection effect. Small, low-mass planets can be detected, but only if they're orbiting close around very well-behaved stars that are observed by the best systems, best telescopes and spectrometers, and teams to discern the data. So if we just had a drop-off here, it would be difficult to know how much is real and how much is observational selection. But this dip here, and then going up, I mean, these are difficult to detect compared to these, but they're easy to detect compared to these. So there clearly must be a real dip there. And there must be far fewer planets of around 20 to 100 Earth masses than 10 and below. And that's what I mean by you need to understand biases. This is eccentricities of the radial velocity planets. The gray ones are ones in multiple planet systems. They tend to be a little lower, but not much. Wide range in eccentricities, except close in. And these are generally circular because tides, these tides, force them into nearly circular orbit. They're very close, so they have strong tides from the star, and this pushing back and forth that I mentioned with Io in my first lecture, Jupiter's moon Io, exerts forces on them and damps down their eccentricity. Okay, astrometry. Planet goes in one direction, the star goes in another. The advantage of this is you get 2 dimensions of the star's motion, so you have an actual mass, not just a minimum mass. This is theoretical curves for our solar system. Again, the blue is just Jupiter. nearly circular. The yellow is the size of the solar disk. So just Jupiter were there, orbiting the sun, that an observer perpendicular to the plane of Jupiter's orbit would see the sun moving around on a circle whose size was almost exactly the same as that of the solar disk. The solar disk is round, circular. Jupiter is slightly eccentric, so you see it bulges out here, but is very nearly tangent there. You add in Saturn, and you get the green curve, and you see that Saturn is making a bigger contribution relative to Jupiter. That's because astrometry, with radial velocity, since velocities drop down with distance, orbital distance, farther away means less radial velocity. With astrometry, farther away means a greater amplitude of the motion. So Saturn is lower in mass, and with radial velocity, it's also smaller because of its greater distance. In astrometry, it's lower in mass, but it partially compensates for that because of its greater distance. And then you have Uranus and Neptune, which are even smaller in mass and even farther away, so they're very difficult to see with radial velocity. But with astrometry, again, they would manifest themselves. Now, they would manifest themselves on timescales of their orbits, which are 84 years and over 160 years. So this is a long time, even for a dissertation project. And so we don't have that yet. Transits. We have a planet, we're in the orbit, and it moves across the star. Now we're not actually, this is what's going on, we're not actually seeing it. What we are doing only is looking at the star. It looks like a point source of light, and the amount of light as a function of time drops when the planet is in front. And this gives the amplitude of the drop, gives the size of the planet relative to the star. The time between drops is the period of the orbit. The way that drop goes down gives us some information on the planet too. Also, if it's at a high, what we call impact parameter. Zero impact parameter is right across the center. High impact parameter is going near the pole. If it's like a sunset, you think of, if you're coming in really directly, if you're looking at near the equator, the sun sets really quickly. If you're doing it up at high angles, high latitudes, it goes very slowly. And that shape can help you discern what the impact parameter is, which is important in deriving other information about the planet. And the amplitude is about the same. It's about 1% for Jupiter and a little under 1/100th of a percent from the ground. That's where you can get Jupiters from the ground fairly easily, but you need to go to space to find Earth. Now, there are planetary transits you can see from Earth. You even see them with your naked eye, or right at sunrise or sunset, or with eclipse glasses at other times. And the right ones are the Venus ones. This is the 2004 transit. There was also another transit in 2012. Who saw either the 2004 or the 2012 Venus transit? I don't have to ask whether you saw any other Venus transits, because before that, the last one was in the 19th century, the 1880s. Now, Venus, I said Venus is a little smaller than Earth. And it's not blocking a lot of the sun's light, but that looks like more than 1/100%. Any idea why? No, not atmosphere. Very close. Right, Lisa. Venus is a lot closer to us than the sun at the time that it transits. It's less than a third the distance. So, while the planet is always closer to the star when it's transiting, it's trivially closer for exoplanets, whereas it's significantly closer for Venus. And therefore, this actually looks more like a Uranus or Neptune transit of an exoplanet at great distance. Now, if you're now interested in observing a Venus transit yourself, you better live really healthy, because the next one is in 2117. But I've got good news for you. Not quite as good as the Venus transit, but the other planet that transits is Mercury. And it transits more frequently, about once a decade or so. It's not observable from everywhere, but happens that the next transit is less than 2 years from now, and the entire transit will be observable from South America. So mark this day on your calendar. What you need, ideally, is a small telescope with a solar filter. You can do it with eclipse glasses. Don't do it with just dark glasses. That is not going to be good for your eyes. It'll damage your eyes. And you can do it with a projection camera, pinhole camera that you use for eclipse viewing too. But I've seen Mercury transits. It's really, for Mercury transit, it's a lot better with a small telescope. But I would hope that the Observatorio Nacional would do something for the public at that, this one. HD 249458b. Henry Draper cataloged stars. That's the number, and then the letter is the planet designator, because the first exoplanets were discovered by spectroscopists. RV is spectroscopist, and spectroscopic binary. They used a notation similar to that of spectroscopic binary stars. There is no A. A is the star. So the first one found is B, then C. If multiple planets are announced at the same time, then the inner one is B, next one is C, etc. I showed some nice little theoretical curves of a transit, but this is a spectrum of the star, and if you look in different wavelengths, you see different shaped transits. This one is the most similar in the infrared to the theoretical profile I showed. In the ultraviolet, it gets much more U-shaped. Anybody know why? Okay, you have to know something about stars, and that is that the limb of a star is darker than most of the disk. It's called limb darkening. And it's basically because we're looking through a longer path length through cooler gas at the upper part of the atmosphere. So it's less bright at the edges, so it goes down. It continues, as the planet gets closer to the center of the star, the transit gets deeper. And in the infrared, the brightness depends less severely on strongly on the temperature, whereas at shorter wavelengths it depends more strongly. So there's nothing fancy about transmissivity of the planet or anything like that. Direct imaging is difficult, to say the least. This is a spectrum, broad wavelength spectrum of the sun. It doesn't account for little features. One of the Earth, Jupiter, and Uranus. And this is 10 orders of magnitude, not 10 astronomical magnitudes, 25 astronomical magnitudes. Huge difference. You get out into the thermal infrared, it's less. But it's still factors of 100,000 or whatever. And the detector technology is not as good out here. And it's also, when you have bigger wavelengths, what you want to do is you want to block the primary with some type of coronagraph. And diffraction requires a larger telescope at these longer wavelengths in order to see the planet near the star. It's not that these planets are so super duper faint. Some exoplanets are substantially brighter than the faintest galaxies observed by the Hubble Space Telescope, or even by big ground-based telescopes. But it's that they're faint things which appear in the sky very close to bright things, they're stellar hosts. So it's like looking for a firefly that's near a searchlight. Except the searchlight is not nearby here in Rio, but the searchlight is in Miami. Okay, you don't have to deal with the curvature of the Earth. But other than that, you know, she's pretty good. This is the most exciting image system. All image exoplanets, other than this system, are single, only one around the host star. This one, there are 4. And in this case, the outermost one is B, then they go C, D, and E, and that's simply because the technology, as technology has advanced, it's been possible to detect planets closer and closer to the star. And these are all about 5 to 12 Jupiter masses, and they're shining from their own heat, thermal infrared. They're relatively young, tens of millions, maybe 100 million years old, around a fairly bright, quite nearby star. The system, in some sense, scales like the solar system in terms of spacing, except everything is a little bigger. The planets are much bigger than Uranus, Neptune, and even than Jupiter and Saturn in terms of mass. Stars a bit bigger. The distances are a bit bigger. Now, we have enough radial velocity planets that we can do some statistics. And these hot Jupiters around stars roughly similar to the Sun, they're around 1 in 150, 1 in 200. Numbers not that well defined. Get a little different results from radial velocity. Gives a little higher number than Kepler. And that's more massive than Saturn, less than 1/10 the distance from their stars than we are from our Sun. About 7% of stars, Sun-like stars, have planets more massive than Jupiter within 2 AU. And many of these planets have highly eccentric orbits. Now, small stars, M dwarfs, which are less than half a solar mass, have fewer giant planets, at least within a few AU, the ones that are detected. So a smaller fraction of those stars have planets. Stars with higher metallicity. Metals, again, for the non-astronomers, are any elements heavier than helium. But it's mainly iron is what people use. So stars with higher metallicity, more likely to host inner giant planets. Stars with one detectable planet are more likely to host multiple RV planets than if you just distributed those RV planets randomly among stars. If you take really Jupiter analogs within a factor of 2 in mass and about a factor of 2 in orbital period, then there are some stars, at least a few percent, host them. More than 25% don't, and we don't really have good statistics to say whether they're somewhat rare or moderately common. And then there's this brown dwarf desert I mentioned earlier in my planet formation lecture. But there are very few companions near stars that are between 15 or 20 Jupiter masses and 70 or 80, compared to the number of binary star companions or the number of companions that are planetary, smaller planetary. And you may have seen a lot of images of exoplanets in the press, on websites, etc. These are all artist conceptions. They're science fiction. You know, there are all sorts of ideas about planets too. This is a tasty one. Now, planets are extremely diverse. And when you have images representing diversity, in the United States, this would be a typical image shown to represent diversity. But this doesn't capture the diversity of planets. Planets are far more diverse than people. A better analogy would be this type of diversity. But even this doesn't go far enough. Let's add to the animals, the plants and fungi. And now we've got a better idea in terms of size and shape and composition, etc. Actually, in terms of composition, these guys are very similar, but compared to planets. But in terms of size, they are bigger range, especially if you include the really small stuff like the spiders, etc. Spiders to trees, big differences in size. Okay, let me go and show you something that can be done for the brightest, biggest, closest in planets. And this is something really special. It's being done now, I think, for one other planet. But this is one of these hot Jupiters. It's within 10 stellar radii of the star. The planet is tidally locked, so that means one face is pointing towards the star all the time. And this is the amount of flux that is seen as a function of time. This is viewed from Hubble Space Telescope. This is the transit. This is the occultation, where the planet goes behind the star and the radiation from the planet goes away. The planet's radiation drops here because you're seeing the night hemisphere. And the amount by which it drops here and how it goes up is used to map the brightness of the exoplanet. And this is the radiation that's actually, see that, longer wavelengths. So it's the radiation, actually this might be from Spitzer's telescope, from one of the space telescopes. And the radiation that's coming from the star. And to fit this, they actually found that the brightest point is not the substellar point, but it's a little bit displaced from the substellar point as a result, presumably, of winds on the planet, the atmosphere of the planet. And this is a nice little cartoon, low resolution. This is and the latitudinal coordinate is just an estimate. And here are views at different angle from this mapping. Okay, this is an early Kepler result saying small planets are numerous. This is an RV result. This is an RV result from just the surveys, one of the highest precision surveys there is. It's a very small fraction of the planets. So and they only observed with this survey stars which were very bright and which were very well behaved so that you get the most precise velocities. And I think they only counted planets within a certain period. And they saw that the number of small planets, I guess they probably didn't actually only count within a certain period, because they see this double hump structure I showed before, except because they're just using the high precision survey, the peak, the smaller peak is actually larger than the big peak. This is still nowhere near as large relative to this peak as you would get in a totally unbiased survey. Totally unbiased survey. Okay, that's it for this lecture, and open the floor for questions. Thanks.
All right, do we have any questions?
Which is the best technique to find planets in binary systems of stars?
Well, binary stars, radial velocity works fine. Well, radial velocity and transits work fine if the binary is pretty well separated. Otherwise, the spectra of the two stars get difficult. Transits work all right, but transits also can detect planets orbiting circumbinary orbits. The transits are the best so far for circumbinary planets. Close to a dozen have been found by Kepler. Whereas radial velocity, they actually, most of the surveys only look at single stars or very distant binaries, but after planets have been found, in many cases, fainter stellar companions have been detected because they've looked much more carefully at the system, and they found stellar companions at 20 to 100 or more AU. So I think those two are the generally best techniques, and they're good here too. Radial velocity should be good. I mean, excuse me, gravitational microlensing should be good too.